Hello students, this is the recording that goes over the last few slides of the project, so slides 14 through 18. So let's go ahead and talk a little bit about impulse. Impulse is something that we reviewed in class. The question here says, in order to decrease the force your object experiences as it hits the ground, the length of time that it takes for the collision to be completed should be shorter, longer, or does not matter. Let's go ahead and talk a little bit about impulse. So remember, we talked about how impulse has two definitions. We said its two definitions are that it is an equation, force times the change in time, or it's also the change in momentum of an object, right? Momentum being how difficult it is to stop the object, so essentially how long it takes to stop the object. All right, now from there we were able to come up with another equation for this idea of our second definition of impulse, which is that impulse also equals mass times change in velocity. So since these two things are identical to each other, we could just set them equal to each other, and this resulted in an equation called the impulse momentum theorem, where on one side we have our first definition of impulse, and on our second side, we have our second definition of impulse. So force times change in time equals mass times change in velocity. Now, I'm not going to go over exactly how to use that equation. That's something that we did in class. But essentially, what we ended up seeing is that assuming that we have scenarios where the mass and change in velocity in a collision are the same, right? So if we're keeping this stuff all the same, then on the left side, as we either change the time or the force, the time, as we either increase or decrease the time, it's going to change the force. So what we saw was if we increase the time and it takes longer for the collision, then it will have less force, or vice versa. If we decrease the time, for a collision to occur, then it will actually have more force and be more painful. So let's go ahead and take a look at the example that we talked about in class. We said, how do the forces compare when the time changes for the same type of collision to be completed? So in this case, we had an old car and a new car, and both of them were identical in mass and change in velocity. Identical mass and change in velocity, meaning that they were in the same crash, right? So they are in the same crash. They slowed down a whole bunch. But in this case, the old car stopped in 0.02 seconds, which is much faster, right? This is a shorter amount of time. All right, and the result is the collision was much more deadly, right? We saw that this resulted in a force of over 1,000,000 newtons, which is definitely way more force and way more deadly. So again, as we have a shorter amount of time, we actually increase our force, because all of that force is occurring during a very short amount of time, which is painful. Now our new car, on the other hand, stopped in 0.15 seconds, which is actually a longer time. And so this crash was slower, right? It took a longer time, and the resulting force was only 180,000 newtons. Still quite a bit of force, but definitely less than our old car and less deadly. So again, as we increase time, we actually result in less force because that force gets spread over a long amount of time, and so that impulse, that change in momentum, gets spread out over a long amount of time, and so it ends up being much less painful. So this is something that we applied in several scenarios in class, but again, our main example was from cars. The whole reason that cars nowadays have airbags and padded dashboards and crumple zones is to increase the time it takes for a collision to occur, because again, we've seen that if we have the same mass, same velocity, same impulse, or change in momentum, we can change the force that we actually feel just based on the time. So what you can see here is if you have a big force, then if you have a small time, then you have a big force, versus if you have a big amount of time for the collision to occur, then you have a small amount of force. So again, increase time in order to decrease force, making things less deadly or painful, less deadly or painful. Okay, so again, the example here that they gave in this picture is that if you were to be stopped by a pile of sand, all right, it would take a long time for this truck to be slowed down by a pile of sand. So by increasing the time it takes for the truck to slow down, we actually decrease the force that the driver feels. On the other hand, if the driver were to have the same exact change in impulse, the same change in motion, but this time run into a wall takes a short amount of time to stop the truck. And so if you have a short amount of time, then you have a really big force and the truck driver might not survive. So again, this is an opposite relationship. In order to decrease force, we want to increase time. All right, so that should help you right here. So if we want to decrease the force, what should we do to the length of time? Should it be shorter, right? Meaning that we should, right, we want to decrease the force. So think about what's the opposite. Should we be making a shorter time? Or should we be making a longer time? Or does time not matter? All right, so that should help you out with slide number 14. Let's go ahead and move on to slide number 15. And slide number 15 and 16 are, 15 and 17 are the results of your experiment. Slide number 15 is if you did the extra credit. So if you did the extra credit. Okay. Keep in mind that in order to actually have results for this, you need to have had your photo. So you need to have your photo / video, otherwise this slide doesn't count. Okay, we do need to actually see your result. Okay, so the question is, did your breakable object survive the fall, right? That was either your egg or your water balloon or your ornament, etc., etc. Those were the options that we gave for breakable objects. You would just say yes or no. And to increase the likelihood your object survives, the time for collision should be shorter or longer. Again, if we want to decrease force, just like we talked about on slide number 14, right, what do we need to do to time? Should we have less time or should we have more time? Again, think about that crashing vehicles. Are we trying to decrease the time or increase the time of collision in order to survive? Okay. What is something that you could do to your contraption to improve the design, even if it was successful? So again, if you want to think about, right, how do we continue to decrease the force the egg feels? All right, that is what you're going to go ahead and put here. Again, as always, IDK, IDC, nothing, etc. are not appropriate answers. You do need to try to give a real answer. All right, so brainstorm a real answer there. Now let's go ahead and talk a little bit about slide 17 before I go back and talk about collisions. So this is if you did the non-extra credit, if you chose the non-extra credit version, all right, which was the 3 objects that you drop, preferably bouncy and ball-shaped. Okay, so let's go ahead and talk a little bit about what happened here. So we have to talk about our types of objects, right? So you're going to fill in your types of objects, right? That could have been a soccer ball, tennis ball, basketball, etc. Whatever your 3 objects were here, right? So make sure you fill those in right here. Then you're going to go ahead and fill in what height you dropped them from. Again, every object should have been dropped from the same height that you chose. You either chose to measure in 100 centimeters, 40 inches, or you used your fingers stacked on top of each other and measured 100 finger widths. So everybody should have just one answer here, right? So if you chose, right, 100 centimeters, you would just write 100 centimeters. If you chose 40 inches, you would just write 40 inches. Or if you chose 100 finger widths, you would write 100 finger widths. And again, here, every object should have had the same, right? So I'll write that in here. Every object should have the same drop height, which is why you only need to write it once. That's why I only have one box here for you. Okay, now the bounce height is then after the first bounce, right? So you mark where your ball bounces back up after the first bounce. Sorry, I should say it bounces back up at the top of the first bounce. Okay, and once you mark where that part is, either like you just put your finger against the wall where it bounced back up, or you marked it with a pen or a marker or something, from there you're going to go ahead and use the same exact units to measure it as you measured with your drop height, right? So if you measured your drop height originally in centimeters, then you should measure your bounce height in centimeters. If you measured it in inches, you should measure your bounce height in inches, and if your drop height was in finger widths, you should measure your bounce height in finger widths. So make sure you use the same exact units, and each ball should have a different answer. Each object should have a different bounce height most likely. All right, so it would be pretty unusual if they all had the same bounce heights. That would be a pretty big indicator that you made up data. So please don't make up data. Don't make up data. Okay, now from here, all you need to do is you're going to go ahead and calculate the difference in our heights. So you're going to go ahead and take the drop height and subtract the bounce height. All right, so you're going to take this, whatever number this was right here, and this number right here, and you would subtract them. All right, so subtract them, and that'll give you your change in height after your bounce height. Same thing, you'll do the same thing for your second bounce. Take this drop height, subtract the bounce height, and that'll equal your change in height. And then same thing for your third one. Take this drop height minus this bounce height, and that will equal your change in height here. Again, the change in height different for each object. Okay, so that'll be your change in height. Now what you should notice is that there is always a change in height. There should always be a change in height because energy is being lost in the collision, okay, as it bounces. Now let's go ahead and talk a little bit about that, because that's going to require us to understand a little bit more about collisions and about this idea of why I put this lost in quotations, because it's not exactly being lost. So let's go ahead and talk a little bit about collisions. So collisions occur when an object strikes another. So for example, when your ball hits the ground. Okay, and there are a couple of different collisions. The first one that we're going to learn about is perfectly elastic collisions. So perfectly elastic collisions occur when objects bounce off of each other, and they bounce off of each other perfectly. So in this case, momentum is always conserved. We've learned about momentum, the change in motion. So momentum, regardless of what's going on in any collision, momentum is always conserved, right? So momentum never changes in a collision. And however, perfectly elastic collisions, in this case, kinetic energy is also conserved. So the energy that each object has is also conserved or saved. So no energy is being lost to any other forms. It's not turning into heat energy, it's not turning into sound energy, etc., etc. An example here would be billiard balls in an ideal situation where the billiard balls hit each other and bounce off of each other, but when they hit each other, they don't make any noise because there's no change in sound energy, they don't make any heat, right? There's no friction, etc., etc. So this would be what we call an ideal situation, which again doesn't happen in real life, but this is the best example we can kind of think of for something that's close to perfectly elastic. Now, when you think about this, you should think about the word elastic, like an elastic rubber band, and how they're bouncy. So perfectly elastic collisions, you should think they bounce off of each other. Now the next type is going to be what we call perfectly inelastic collisions. So inelastic is the opposite. This time they do not bounce. So this time the objects actually stick together. Now I already talked about momentum is still being conserved. The mass and overall velocity of the system still remains the same. However, this time we are losing the maximum amount of energy to what's happening, right? So the maximum amount of kinetic energy is actually being lost, which when we say lost, it's not actually like disappearing from our universe, it's just being converted. Again, you can't actually lose energy, but it is being converted and changed due to joining the two objects together. Okay, so this time the objects are gonna stick together. An example here is a ballistic pendulum. What you can see here is we have a object shooting towards this box right here, this block right here, and then they actually stick together, and as they stick together, their motion and their mass combine together, okay? So the momentum is still the same, mass and overall velocity will still average out to be the same. However, it's losing a lot of kinetic energy because the objects are joining together. This idea of joining or coming together is going to lose kinetic energy. It's going to change it into something else. So it's going to change that energy. All right, so we're losing kinetic energy because it's being turned into something else. Now, again, a good way to think about this is the prefix for inelastic. The prefix in means not, so this means it's not elastic or not bouncy. So again, in this case, perfectly inelastic collisions, they are not bouncy. Now, the reality is that no collision on Earth is perfect. So there are no real collisions that are perfectly inelastic, meaning they stick together. And there's no collisions that are perfectly elastic, which is where they bounce off. Okay. Instead, the third category is basically everything. So this is real life where we have inelastic collisions, but they're not perfect, right? So again, this is not perfect, right? So I know that's a little bit confusing because two of them use the term inelastic, but again, one is perfectly elastic, one is perfectly inelastic, and now we just have our third one, which is inelastic and not perfect. So inelastic means there's still this idea that there's some energy being converted, right? So some kinetic energy is being lost or converted, but not all of it, but not all. Like it happens in inelastic. Or sorry, I shouldn't say all, but not the max. Like what happens in a perfectly inelastic example. All right, so here we go. So momentum again is still being conserved. All right, so even though when things collide, again, mass velocity overall averages out to be the same. So momentum is being conserved. However, in this case, some kinetic energy, again, is going to be lost or converted to other forms, but not the max amount, again, so it's not perfectly inelastic, but it is going to be a little bit inelastic, right? So the other forms that it can be lost to are sound, heat, or material deformation, which means like the material changes shape. And an example here would be car crashes. So car crashes result in a lot of sound energy. That's a type of energy. So kinetic energy is changing into sound energy. That's why you hear the crash. It also results in a lot of heat energy, right? If you touch the metal after a crash, the metal of a car will be much hotter because some of that kinetic energy was converted or changed into heat energy. And it also results in material deformation. Some of that energy goes into changing the shape of the cars. That's why cars actually crumple. All right, so these are all examples of what we just talked about: sound, heat, and material deformation. So you want to think about this as like the in-between type and the real type, right? It's also the real type that most of our collisions on Earth actually fall under. Again, nothing's going to really be perfectly inelastic, nothing's going to be perfectly elastic. Things are instead going to fall in between and are inelastic collisions. Okay, so that's going to help us with this last question right here. Based on your understanding of inelastic collisions, what are 3 reasons your objects lose energy, resulting in their bounce heights being lower than their drop heights? Again, every bounce height should be lower. Bounce height for every object should be smaller than drop height. Otherwise, you did it incorrectly. Okay, so your drop heights should be 140, 100, your bounce height should be smaller than all of those, okay? Now, the reason why is based on what we just talked about, all right? So you can literally copy these, right? So you can say that it's due to sound, heat, and material deformation, right? The sound of the ball bouncing, due to the sound of the ball bouncing, of the object bouncing, some heat when the object bounces. All right, so if you were to bounce a ball several times, you would actually begin to feel that object warm up. You probably won't feel it after the first bounce, but after several bounces, you would feel it. And then finally, the material deformation. So the object changes shape momentarily when it hits the ground. All right, so that is all reasons why the bounce heights are lower than the drop heights, and you can feel free to copy these because these are things that we defined in class together, that we're defining together. Sorry, let me try to clean it up here. There we go. All right, so feel free to copy what I gave you right here. Okay, so again, feel free to copy that. Perfect. All right, so let's go ahead and talk about slide number 18. So slide number 18 is just a reflection. You need to talk about something that went well and something you can do to improve on future projects. As always, I don't know, I don't care, or nothing are not appropriate answers. And you only get credit if you actually finish the project. So you can't just skip things in the project and then do the reflection and expect to get points for the reflection. You do actually have to do the entire project. All right, so there's a reminder right here for you. All right, so let me go ahead and show you then how to submit the project. So the first thing that you need to do is, if you're in Google Slides, you need to first download your project either as a PowerPoint or as a PDF. So you would go to File, Download, and PowerPoint or PDF, right? So File, Download, PowerPoint, or PDF if you used Google Slides. Obviously, if you already used PowerPoint, if you downloaded it as a PowerPoint in the first place, it's already there as a PowerPoint. So let me go ahead and show you. Again, File, Download, PowerPoint, or PDF, either one is fine there, and save it to some place you can find it. I'm just going to save it to my downloads folder for now. And then you're going to go ahead and go to your course page, and you're going to go to your grades tab, because everything's always in your grades tab. So make sure you go to your grades tab. And what you will see here is, if you scroll down, you'll see the egg drop, right? And that is your indicator that this is the drop project. And you'll see the submission folder right here. So make sure you go ahead and then click on the submission folder. And when you scroll down, right, so you're going to go to the grades tab and find the submission folder. Then you're going to go ahead and click add a file and follow the directions. So when we click add a file, right, let me go ahead and show that to you. Add a file. You're going to get your file from your computer, obviously, because it's saved on your computer. So my computer, and then upload. And mine was in my downloads folder, so I would go to my downloads folder. Here it is right here. And then once it's all loaded, the green bar has loaded, you can go ahead and click add. All right, so again, click add a file, follow the directions, and finally submit. All right, so you'll go ahead and you will click submit, and you will see that it gives you a message saying that it has been submitted. Right, so it says file submission successful, and that's how you know that you submitted it. All right, thank you so much, and I will talk to you later.